Hello everyone, I'm Zihao Yang. Here's my presentation of my Rack Power Resume Q&A application. First, let me briefly introduce the objective of this project. I want to build a Q&A application of the resume, but if I just use the large language model to give the prompt and get an answer, the large language model might not have some domain knowledge of each resume of each person because the resumes can be updated quickly and there's a lot of resumes. So I want to build and deploy a rack powered Q&A application to enhance the response of the uploaded resume. For this project, it can be separated into two parts. The first part is that I leverage the semantic trunking and vector database to efficiently retrieve the relevant resume sections and generate some response with the GPT model. After we get the retrieved context, we add it to the prompt of the large language model to provide some relevant information about the query so that it can be used to enhance the general response. Based on this part, it can efficiently prevent the hallucinations of the GPT model based on the because it might not have some domain knowledge of each resume. For the data, to build a vector database, we use the embeddings of the trunkings of the uploaded resume. For the pipeline of for the pipeline of the the demo, for each user, it can upload a resume, and the application can convert the resume to the trunkings and to convert all of the trunkings to different to the embeddings, and to save all of the embeddings to the vector database. And here is the sample resume. It is my resume. Let me briefly show the pipeline. The first part is the trunking part. First, we do the test extraction and preprocessing. We use the library PyPDF tool to extract the raw text from the uploaded PDM resume, and we remove some unwanted characters and normalize the white space. I use the spaces in Core WebAssembly model to tokenize the sentence text into sentences. After that, we do the trunkings of all of the sentences. First, we encode each sentence into dense vector representations, use the sentence transform model, and we measure the semantic similarity between the two consecutive sentences using concise similarity. We group the sentences into chunks if their similarity exceeds the threshold. Default is 0.8 to ensure that there is the contextual coherence. And we limit its chunk to a maximum of predefined number of sentences. The default is 5 to ensure that there is the optimal retrieval graduality. After the trunking part, here we jump into the vector database part. We need to build a vector database based on the trunkings. First, we need to convert each trunks to the vector data to the embeddings. We use the same model in the trunking part of the sentence transformer to help keep the coherence of the trunking and the embedding part. And this embedding captures the semantic meaning of the text, enabling similarity-based search. And these embeddings are stored alongside the corresponding text chunks for efficient retrieval. And to help build the vector database, we use the ChromaDB to store and manage the text embeddings. For each trunk, it is stored with the document ID, text content, and vector embedding. This structure storage allows the fast and scalable similarity searches. For the final part, for the third part of the pipeline is the retrieval part. For each query, when a user submits a question, the system first preprocesses the query to remove unnecessary characters or formatting issues. And then this query is converted in embedding using the sentence transformer model. The model is the same as the trunking and embeddings to build a vector database, so that we can ensure that it can be compared with the store embeddings. Because if we use the different embedding model, though we might have the same embeddings, the meanings can be different. So there's no use to use the concise similarity to compare the core embeddings with the storage embeddings. And then we do the vector similarity search in the ChromaDB. We use the core embeddings to search for the most relevant resume chunks in ChromaDB. We use the concise similarity to retrieve the top k most similar chunks. The default is 3 to mirror the semantic closeness. This can ensure that the retrieved context is highly relevant to the user's question. After we get the relevant information based on the query, we add it to the prompt. We ranked the retrieved chunks and combined the structured context and passed into larger model in the prompt. And this context where retrieval helps eliminate the hallucinations by grounding the model's response in real and relevant information. The last part of the pipeline is the larger model response. First, we construct the prompt, use the structured prompt template to guide the larger model to generate an accurate and concise answer. We ensure that the larger model can focus only the retrieved data to reduce the irrelevant responses. And we use the GPT-4 as the larger model because it is robust and it can generate a natural large response based on both query and the retrieved context. Because it is application of the Q&A, so it's pretty important to make the response highly as the style as the natural language. And the GPT-4 is very good at it. And we set some parameters like the temperature and the max tokens to control the response creativity and length. And I want to introduce the three different very important model in this project. The first is the sentence embedding model. We use the sentence transformer or mini F2V2 to convert text into vector embeddings. It can capture the semantic meaning for efficient similarity-based retrieval. For this embedding model, it is used in the trunking part and embedding part to build a vector database, and it also used in the embedding part of the query. And for the tokenized model, we use the Encore WebAssembly. It is small-sized English NLP model from SPACY. It is designed for efficient text preprocessing. It provides the tokenization with the minimal computational overhead. For the larger model, we use the GPT-4 because it is robust and it can dynamically construct the prompts with the retrieved text, and it can also ensure the response are grounded in the uploaded resume to minimize the hallucinations based on its inertial characters of the GPT-4. For the performance evaluation, first let me show the demo to manually examine the retrieval efficiency, the response accuracy, and user experience. First, let me upload the resume. The application is doing the trunking, the embedding, and build a vector database. So I can answer a question. What is the person's undergraduate school? Okay, here's the question. And let me see the log to see the retrieval efficiency. We can see there's two top trunks. First, it retrieved the information of this person, and in the second trunk, it efficiently retrieved the undergraduate school of this person of the Tongji University, and we can see the response. The person's undergrad school is Tongji University in Shanghai, China. So the response accuracy is very good, and the retrieval efficiency is pretty good. And for the user experience, we can see that the demo is easy to use, and it can generate the relevance data. And for my manual test, I generate 10 questions and to give to the application, and the applications can answer all of the 10 questions correctly. And from my perspective, I observed that the retrieved efficiency is very good. Here's all my presentations, and thank you for your listening.